Hello, this is Mr. McGovern. This is the 9th video in the NCEA electricity series on inductors, and we're finishing off the inductors topic with an NCEA question. So this is from 2022. It's question 2, and we're going through A all the way through to D. So David investigating inductors and magnets. He uses a 1.6 Henry, so that's L, 22 ohm inductor, connects it to a 12 volt power supply. The inductor can be considered as a pure inductor in series with the resistor. So they're basically saying the inductor can be considered as an inductor and a resistor beside each other. Calculate the circuit current after two time constants, once the switch is closed and the current begins to flow. So the first thing is we're going to get our graph right, and our graph grows until it reaches our steady state value. Remember, with the growing value, instead of the 37%, we're going to deal with the 63%. And then after two constants, it's 63% of what's remaining. So let's start by working out Imax, because then we can work out 63% of that. So Imax is just the steady state value, which is just V equals IR. Rearrange it to I equals V over R. We've got our 12 and 22 ohms, and that's 0.545. I'm going to put that on the graph up here. So here it is, so I've got what I've got, and if I do 63% of that, so that's one time constant, I get 63 times 0.545, and that's 0.344, so I'll put that on the graph as well. After two time constants, so what they're asking for is 63% of the remaining, so it's from 0.3 up to 0.5. So what's 63% of that? So what I've got to do is I've got to find the difference, the value between these two. So that's Imax minus this one, so that's the 0.5 minus the 0.3, so that's the value between here, and so I can find 63% of that. So it's jumping 0.2 from here to here. So what's 63% of that 0.2? And that's 0.1. So above the first red line I'm going 0.127, so I add my 0.3 to 0.127, and that's my last value. 0.47 is the answer, and that's a merit question. Now, to be honest, that's looking at the rest of this question. This is probably the hardest question in the whole thing, and it's worth the merit. When you get to the excellence one, you'll see, well, that was really easy. So I don't know how they got that, this being the merit and the last one being the excellence, but you'll see. Okay, calculate the voltage across the inductor and the voltage across the resistor once the current's steady. So once the current's steady, there's no change in flux, so there's no back EMF. So again, you just got to know these graph shapes, right? So the values are 0 and 12, but I'll just show you on the graph. So the resistor, after a steady state, goes to its full value, 12 volts. That's why that's 12 volts. After its steady state, the inductor has no more back EMF, so it's down to 0, and that's where the answer 0 comes in. So that's your achieved. You didn't have to draw the graphs, but seeing the graphs helps me answer the actual question, if that makes sense. Once the currents reach a steady value, a switch is open, the current falls to 0 in this amount of time. Calculate the size of the induced voltage, calculate the direction of the induced voltage across the inductor. Let's do the size first. So back EMF or self-inductance, inductor, change in current over time. I had my current, remember I calculated it in the first one, 0.5, and this is the time they gave me. 2.5 by 10 to the minus 2 is this number, times by 1.6 Henrys, and that's about 35 or 34.9 volts. Now, the direction of the induced voltage, direction of voltage doesn't really make sense. The polarity of voltage, I guess, is what they're asking. Let's look at Lenz's law. So this first one is Faraday's law, it calculates the voltage. Lenz's law tells you the direction of the current. And it says nature abhors a change in flux. So how's the flux changing? Well, it's decreasing. It's going from full field to nothing, right? And it doesn't like that change. It doesn't like that change in flux. So it doesn't like it decreasing. So it tries to make a field that maintains that flux, right? So it's trying to make a field in the same direction as the field that's already disappearing. So if it's trying to make that same field, it's making current in that same direction. And so to do that, the voltage is going in the same direction or the same polarity as the battery or the power supply. That was also worth a merit. I guess one for the answer and one for the direction. And then the last question says the resistor is replaced with a resistor which is twice as big. The switch is then closed. Explain quantitatively, so with numbers, the changes that will take place for the maximum current, the time constant, the energy stored. So we've got a formula for each of these. So V equals IR is the steady state current, and we can just do a calculation if you want. Yeah, just 12 volts, same as before, over 44, and that's half as much current. Now, instead of doing the calculation, because I'm double the resistor, I'm now at level 3, I can sort of see the algebra and realize double resistor means half the current. And so in this case, the voltage is unchanged, so I can just do the algebra. So both of these answers would have been okay. I'm going to go from now on with this sort of answer for the last two questions, of just knowing that if I look at the formula as an inverse relationship, that means if I double one, I half the other. So let's look at the next formula. This is the time constant. What happens to the time constant? Well, that's also an inverse relationship, right? So if I double R, I half T. Cool. And then finally, let's look at the energy stored in the inductor. So the energy stored in the inductor is L times I squared. L's unchanged. But remember, we found that I before was halved, but there's a squared in here. So because I is halved, and I've written this is meant to be energy instead of I is halved, the energy is going to be, because it's squared, it's going to be half squared. And half squared is a quarter. So the energy is this quarter is big. And that was an excellence question. So there we have it. 2022 A, B, C, and D.